Hi everyone, my name is Giacomo and today I'm here to give you a talk on elliptic curves and their application to cryptography. The main aim of this talk is to be able to give a thorough introduction to somebody who knows either little or a bit about elliptic curves, while also being formal enough that you can look up stuff on your own and being non-trivial. So we're going to be looking at some stuff which is, I think, quite interesting. This is a kind of talk which I would have liked to give myself when I started delving into the field, so I hope it will be of assistance of anybody who's interested in starting elliptic curve cryptography and can serve as a reference for some of the main concepts which might be helpful for that kind of introduction. So as motivation, I'm going to start with a quote from the great Serge Lang, in which he said that it is possible to write endlessly on elliptic curves. And it is completely correct. Elliptic curves are a huge research field in which touches a lot of different disciplines such as computer science, mathematics, and cryptography. There are just a lot of applications and a lot of ways you can use them, and recently they've really risen into prominence with cryptography and elliptic curves, which is almost everywhere now. If you're using cryptography on the web, which everybody is in some way or another, more or less, most of the key exchanges that you're doing are elliptic curve diffie-Hellman, and signatures are often done via elliptic curves as well, via the BLS, which are both two things that we're going to be looking at. In particular, just to give you some figures, around 70% of the exchanges that are done by TLS, which is the primitive which enables us to navigate securely on the web, are made via elliptic curve diffie-Hellman. And the number is only poised to rise with the introduction of TLS 1.3, which would make even heavier use of diffie-Hellman schemes and elliptic curves as well. You might have also heard that the quantum computers are coming, and they're kind of the boogeyman of public key cryptography. So a lot of the schemes that we're using nowadays, they would break if a quantum adversary powerful enough were to be constructed. Luckily, elliptic curves, they're very flexible, and they actually provide us as well to get out of this situation. In particular, there's what I think is the coolest post-quantum cryptography proposal, which are the supersingular isogeny diffie-Hellman and the supersingular isogeny key exchanges, which are two primitives which are being looked at now to enable us to transition to post-quantum. For some reason, NIST does not seem to think that coolness is an appropriate criteria to standardize something, but I'm sure they'll change their mind. It's just a phase. Finally, but of course not least as a thing, elliptic curves are very fascinating mathematically. They have a lot of structure, they have a lot of application in number theory, they have a lot of applications in algebraic geometry, in arithmetic geometry. So from my point of view, they're very elegant, which is something which I value very early, and which makes them worthy of study already in themselves. Of course, the fact that they also have a lot of application is something, it's just a cherry on the cake. So the talk will be, the outline of the talk will be as following. We're going to be starting with some historical notes. We're going to be giving some ideas of where elliptic curve originated. We're going to be talking about Diophantine equation and the sorts. Then we're going to introduce the mathematical background, which is going to be required. This is going to be kind of light. It will just be fields and extension fields, but it is meant to make the talk as self-contained as possible, hopefully. And I'll of course provide timestamps on the video, so you'll be able to skip this section if it is something that you already know about. Next, we're going to be looking at what the group law and addition on elliptic curves. It is something which essentially is not exactly trivial to do, but gives a lot of properties to elliptic curves. It allows you to add points and with the added structure, so giving to a geometric object like a curve an algebraic structure, something which has a really powerful, which is really powerful. Okay, so now we're going to move towards the outline of the talk. So, okay. Okay, now we're going to move towards the outline of the talk. So we're going to be starting with some historical notes, which are essentially just a short survey of some problems related to elliptic curves, which elliptic curves have had a contribution in their development, or which had a development in the introduction of elliptic curves. So I'm going to be talking about the Diophantine equation and the like, and the origin of the name elliptic. It's going to be just a very short introduction. Next, we're going to be looking at the mathematical background. This is again going to be quite short. This is going to be just a refresher, hopefully, on some of the basic primitives that are needed to understand elliptic curves, and which I've added there because I want to make the talk about as self-contained as possible, but of course I'll make timestamps, so if you want to skip them, they will be very easy to do. Next, we're going to be looking about additional elliptic curves. This essentially is a way of giving an algebraic structure to elliptic curve, which is one of the reasons why it is so powerful, which they are so powerful. Essentially, by giving this algebraic structure to a primarily geometric objects such as elliptic curves, you're able to do a lot of very cool stuff, and it is something that we're going to be needing for most of the schemes that we're going to be looking at. Then we're going to be have our first deep into cryptography. We're going to be looking at some assumptions. We're going to be talking about the way that the cryptographic process works, and we're going to be talking about discrete logarithm and Diffie-Hellman, which is the algorithm underpinning most of our key exchanges today. Next, we're going to be looking at something else which elliptic curves enable us to do, namely pairings, which are essentially what's called a multilinear map, which is non-degenerate. And essentially, these are quite peculiar objects because they make some problems that in other groups are hard easy, but they also allow us to make very efficient signatures. So that's quite an interesting thing. So we're also going to be looking at what are called BLS signatures, which are efficient and aggregatable signatures that are used quite a lot today. Next, finally, we're going to be looking at isogenies, which are the fundament of the post-quantum scheme which I was talking about. This is going to be a quite beefy section, quite theoretical, but we're going to build it up from the bottom up until we get towards the SIDH post-quantum Diffie-Hellman scheme, which is going to be quite interesting from my point of view. So I hope you're looking forward to this, and we can start getting into the nitty-gritty now. Our trips start from the context of Diophantine equations. So these are equations as the ones that you might have seen in grade school. The only difference is that we are trying to find a solution over not over the real numbers or the complex number. We're trying to find solutions over either the integers or the rationals. This particular equation which I've put here on the screen is one which is very famous. It is the one which appears in the statement of Fermat's theorem. Why are we interested in Diophantine equations? Well, it is because essentially they're very hard to solve, like in general. As you might have known, Fermat's theorem was only proved very recently by Wiles, and the solution is something which has been eluding mathematicians for a while. And this is something which happens a lot in Diophantine equations. It's quite interesting how changing just the base ring or field in which you're working actually changes completely the difficulty of the problem. So, for example, like all the Diophantine equations are trivial if you're working over the real numbers, because we have efficient way to solve them. We can use the approximation techniques, for example, which work very easily. If you're trying to find integers and rational solutions, then it starts becoming very, very hard. And in fact, it is so hard that it was proven that we cannot hope to have a general method for solving Diophantine equations. This is something which Hilbert called the stamp problem, and it was proven that it is actually undecidable. So there is no finite procedure that we can run, no algorithm that will take a Diophantine equation and then we'll be able to show whether it has solutions. So that's kind of disconcerting because it shows us what the limits in our reasoning are, but it still gives us a lot to do. Particularly, there are two main things that we want to figure out about Diophantine equations. We want to find out whether they have solutions, because some of them will not have solutions. And if they have solutions, we want to find out how many of them have them. Do they have one? Do they have few? Do they have infinitely many? That are the kind of thing that we would like to figure out about Diophantine equations. So the general case is completely hopeless, but we can move towards some simpler cases and see if those have a simpler structure which allow us to make progress. So the simpler case that we can look at is the case in which we have one variable when we have one variable. These equations, they take the form which are shown here, and essentially this is the easiest case that we can possibly have. And in fact, there is enough that we can solve them in general. So in particular, we can prove this lemma, which relies on Gauss's lemma. And the idea is that this gives us a list of possible candidate rationals. And once we have this list, we can just simply check all of them to figure out whether we have a solution. And in fact, you can even do this a bit more efficiently. Something that you can do is find the zeros of this polynomial numerically or using like other methods. And then you can just try to figure out whether you can express these roots in this formula which are written here. So I don't want to go too much into it, but that's the kind of thing you can do. And that means that the one variable case is very, very easy to solve. You can always find whether there are rational or integer solutions. And that is something which we like. The natural net step, the natural net problem to solve is when we have an equation in two variables which is linear. In fact, you can just look at this and figure out that there are infinitely many rational solutions, because essentially if you essentially you can just rearrange and figure out the rational solutions. And in fact, if you have done a bit of number theory, this expression is something which comes out quite often, especially in the context of Bézout's lemma, and this leads you to conclude to the following theorem. Essentially, this provides a very simple criteria which allows you to figure out whether this equation has got integer solutions. And if it has integer solution, it will have infinitely many. So you can just simply compute the GCD of the two coefficients and see whether the constant term is divided by the GCD of these two coefficients. So this case is even easier than the previous one, which is nice. Where things gets a bit more complicated is when we start increasing the degrees. So this is a general equation of a polynomial in two variables of degree 2, and in fact this is somewhere where we can already do progress, but it's a bit more complicated. So what you can notice is that this is the equation of a conic. So something like a circle or an ellipse or an hyperbola. And in fact, we can find a solution in a geometric way. So, well, we can find a solution in a geometric way, but it also needs a bit of algebra. So I'm going to divide this in two steps. So the first step will be the geometric one. So essentially, if we have a rational point on this curve, so if we know one point which satisfies the equation, then we have the tools to find all of the other ones by geometry. I'm not going to go too deep into it, but the main idea of it is that you can essentially draw a line from this point and then project the conic onto it. And essentially, by the way that polynomials work and the intersection works, if you will essentially, by going through this line, you will get all the rational points on the conic. Okay, cool. So if we have a rational point, then we're able to find all others. But how can we figure out whether one rational point exists? Well, the solution is to use what's called the asset principle, or the global to local. The local to global. The idea is that if you have a conic and this conic has got solution in the reals and it's got solution in the p-adic numbers for every prime, then you also have a solution in the rationals. And essentially this yields a procedure which allows you to check whether one conic has got a point. So that allows us, with a bit of work, to figure out whether the quadratic two-variable case has got a solution, which is quite nice. Do we have the same luck with the two-variable degree 3 case? Unfortunately not, but this is an interesting case. In fact, this is what we will see is the general form of an elliptic curve. there are something which we already, we can figure out. So we can take an analogous view to the previous problem. So we can have these two steps, the generation step and the finding a point on it. And the generation step kind of works. It's a bit different. There's this beautiful theorem by Mordell, which essentially, if the curve is nicely behaved, then you can essentially generate all the rational points on it from a set of from a finite set of points on the curve. And say how big this set is, but it doesn't say what the group operation is, but it is something which we'll see later on. Unfortunately, there is no equivalent of the local to global principle for elliptic curves. So that is why this case is not as nice as the one that we've seen beforehand. Now a note, why are elliptic curves called ellipses? Sorry, why are elliptic curves called like that? It has nothing to do with ellipses. Well, they have something to do with ellipses, but they're not the same thing. The main difference is that elliptic curves are of degree 3, while ellipses are conics, or they are of degree 2. So they are not the same object. The reason why they were originally called like this, it seems to originate from the fact that when you compute the arc length of an ellipse, you get a kind of a gnarly integral, which has of a function which has the form of y is equal to the square root of a polynomial of degree 3. If you square both sides, you get something which is similar to the Weierstrass transform of an elliptic curve. So that is where the name is thought to have originated from. Okay, so this concludes kind of the historical motivation. I tried to keep it a bit brief. And now we can move towards some of the mathematical background. And in particular, we're going to be starting by talking about fields. So fields are the basic building block that we're going to be looking at, and they're essentially things that you can add, subtract, multiply, and divide. Some examples include the real numbers, right? You can sum them, you can divide for anything which is non-zero, and that works. Or for example, the rational numbers are also a field. A bit more complicated, if you have a prime p, the ring of integer modulo p is actually a field. Something which is not a field, to get something which is not, is for example the integers, because in the integers you cannot actually divide. There's for example, if you have 3, you cannot divide it by 2 because you will get something which is not an integer. So the integers are not a field. So cool, like I talked, I'll give you a couple of examples of fields, but there are some which were, in particular, our cryptography were mostly fond on, and those are the finite fields. So, as I said before, the integers modulo p are a field, and it is of finite size. And we're mostly interested in those because they have efficient representations. Like, if we were dealing with an infinite field, like for example the reals or the rationals, when you're doing operation with them, their size can grow quite a bit. They can actually become unbounded. For example, if you just take the number 1 as a rational and you just sum it to each other, then you can get numbers which become very, very big. Or if you take the number 2, you raise it, it just becomes big very quickly. If instead we're working with finite fields, then we know that the size of an element is always of a fit size, and that allows us to essentially store them in memory efficiently and manipulate them efficiently. And luckily, we have quite a variety to choose from. In fact, we have this theorem which characterizes uniquely all the finite fields. Essentially, if you have any prime p and every positive number, then there will be a unique field of size or order p to the n. And we're going to show how we also can construct them quite efficiently. If n is equal to 1, then we simply take the finite field to be the integers modulo p, as I was saying before, those are a field. Otherwise, we can write them as a quotient. We can essentially take, to take the finite field of order p to the n, we simply take the ring of polynomials with coefficient in the integer modulo p, and we quotient it by an irreducible polynomial of degree n. If you remember a bit of commutative algebra, since f is irreducible, then the ideal that it generates will be maximal, and so the quotient will be a field. What this means in practice is essentially that elements of elements of this field are a list, or which can be thought of as a polynomial. Addition is done component-wise, and for multiplication you multiply as you would do polynomials, but then you also reduce modular polynomials. So for example, if the polynomial were x to the n minus 1, then you would replace every term with which has a degree greater than n with 1. For example, if you had n is equal to 6 and you add a term which is x to the 7, it will become just x. So that's the kind of thing you can do those operations quite efficiently in hardware, and nowadays I think they're also supported by most CPUs depending on which operation. So the main takeaway is that for finite field you can do operation very efficiently, and they are the building block for almost everything that we're going to be doing. Next we're going to be talking about characteristics. So a characteristic of a field is essentially the list of, so essentially it's something that we get from adding ones quite a lot of times. So the idea is that if we have a field, there will be an identity, and we can we can start adding it to itself until we get to 0. In some fields that will not happen. For example, in the reals, if you keep adding 1 to itself, you will just get increasingly bigger numbers. So in that case, we say that the characteristic is infinite. For other fields, like for example the integers modulo p, if you add 1 to each other p times, then it will vanish. You will get to 0. That actually shows that if we have a finite field whose order is p to some power, then its characteristic will be p. So why is the characteristic of a field important? Well, essentially, fields they play nicely with each other only if they have the same characteristic. What this means is that if there are two fields of a different characteristic, then there will be no homomorphism between them, which essentially means they're not particularly interesting, like from some view of category theory. But that's not something that you need to know about. Something else that is important about the characteristic is that if you're in a field of characteristic P, then what's called the freshman dream holds. Essentially, it's something which happens quite a lot when you start learning mathematics, is that you have to take a square of two numbers, right? You have x plus y squared. And something which people sometimes get mistaken is that they just evaluate this as x squared plus y squared, forgetting the plus 2xy term. In fact, those people would be correct if they were working in characteristic 2. And in fact, more generally, if you're working in characteristic P, the sum of the pth power of the sum of two elements is the sum of the pth power of the individual elements. So if you have x plus y to the p, it is equal to x to the p plus y to the p, which is something which is quite interesting and important, especially in the context of Frobenius endomorphism, which we'll see later, maybe, I don't know. Yeah, we'll see them later. Next we'll be looking at field extension. So this is the first thing which is a bit more on the nose, but essentially the idea is that if you have two fields of the same characteristic, of course, because otherwise they won't interact, if there is an homomorphism between them, we can essentially see the smaller field as a subfield of the larger one. So what this means essentially is that you can look at a field and it will have inside a copy of the smaller field, and we call these field extensions. So these are quite important, especially in the context of Galois theory. But for us, what they're really interesting on is that if you have an elliptic curve defined modulo p, then you can also have you can also think of it think of the integer modulo p as something inside of the finite field of order p squared or p to the 3, which is something which I have here on the slide. So yeah, I was saying, like, this is the kind of inclusion that we're looking at. So for example, the rationals are a subfield of the reals, so the reals are a field extension of the rationals, and so on. Something that we are interested in a lot in field theory is also algebraic closures, and more generally the roots of polynomial over a field. So the main idea is that when you have some polynomial over a field, it is desirable that you're able to solve. So you want the roots of that polynomial to lie in the field. That is not in general true. So for example, if you look at the rationals, you can look at the polynomial x squared minus 2, right? Whose roots are plus and minus square root of 2. And despite these polynomials being over the rationals, the two roots are not in the rationals. So if we have a field in which for whichever polynomial we look at, all the roots are in the field, then we say that the field is algebraically closed. And if in fact we can actually take any field and construct something which is called algebraic closure, which is the smallest extension of the field which is algebraically closed. In particular, something that you can look at is that the algebraic closure of a field must necessarily be infinite. So in particular, it is bigger than all of the, so if you're looking at for the finite fields, you will, the infinite tower of finite field will be contained in the algebraic closure. Yeah. You can also approximate, if you want, the algebraic closure a bit. For example, you can take to have a field, imagine that you have a base field fp, for example, and you want to get a field which is closed, in which the roots of all polynomials of degree at most n is in the field. Well, then you can take the field f to the p to the n factorial, and they will be close enough. It will be very big, but it will still be finite. So that's a way that you can approximate the algebraic closure, which is there mostly for content. But this is all the prerequisites that we needed. Hopefully I haven't confused you too much, but essentially, yeah, this is the prerequisite. Now we can start getting into the nitty-gritty, and we can do that by starting from representations. So essentially, if you have you've seen before the formula for an elliptic curve, which look kind of terrible. It had a lot of terms, a lot of things. Well, in fact, if you're clever, you can get this to a much nicer form. Essentially, you can start by relabeling the variables, shifting things around, and get it to a nicer form, which is this one, which is already much more manageable. And then you can also do that a bit more in case the characteristic of the field is not 2 or 3, to get it to this form, which is called the short-bias transform, which I think you would agree is much easier to manage. Yeah, I want to mention that this is the most commonly seen form of an elliptic curve, especially for the academic world when you're trying to learn about them, and it is the one that we'll be using for most of our talk. But I want to mention that other models exist. For example, there are Montgomery curves, which are very much used in cryptography because essentially their addition formula, they only rely on the x component, not on the y component. Or there are Edwards curves which allow for something which is called a complete addition formula, which essentially means that you don't have to handle very many cases. And there are Legendre curves which just look pretty from what I've understood. I still need to research them a bit more thoroughly. Okay, now we can get to the piece of resistance. We can start introducing what an elliptic curve is. So we take any field, and an elliptic curve is given by the set of points which satisfy their Weierstrass equations. In particular, we can take all the points which satisfy the equations, and we also tack in this extra point, which is called the point at infinity, which it's got a quite interesting story. Essentially, when we start talking about elliptic curves, you can take the pragmatic cryptography way, which is the one which I've been talking about here, or you can do the algebraic geometry way, in which you can essentially define the elliptic curves as a curve in a projective space. Projective space is something which is a bit difficult to visualize, but essentially it is same as it is the space that you like and love, added with some points at infinity. And essentially, when you're taking these projective coordinates, they're called, which in this case they would be x, y, and z, and you dehomogenize them to get to the affine case, you also have to add a pointer in infinity, which makes things a little bit more complicated with addition formulas, but it is quite elegant if you know where it's coming from. But we don't need to know too much about it. Something that you might also notice is that the group of elliptic curve point is defined over extensions of K. Essentially means that if you have an elliptic curve over some field, you can also look at the group of points over extension fields of it. So for example, something that mathematicians like is to have curves defined over the rationals, and then also look at their groups over their reals or over the complex numbers. Us in particular, we're going to be looking mostly at the finite case, so but it is something which is important now, especially because the field over which a curve is defined, and it's something which can have quite a bit of difference. So here is our first look at an elliptic curve. This is a kind of a typical one. You can see a couple of features which are distinctive. So for example, you have a symmetry over the x-axis, right? So that essentially comes from the fact that the y is symmetric, and also you have that the curve goes to infinity and minus infinity as x increases. So that's a general form of an elliptic curve, but something that you want to notice is that this is an elliptic curve of the reals. In general, the curve that we usually look at, they're not as nice. This is what the same elliptic curve looks over the integer modulo 89, which is much more messy. So you still have a bit of symmetry, but it's much more complicated. When we work with elliptic curves, one of the nice news that we have is that we can think about stuff geometrically from the point of view of the reals number, and then by switching from the reals number to the finite case, we can get results usually. Not in all cases, but in some cases that is quite handy. So you will see when we're looking at the addition formulas, we will think about them geometrically from the real case, and then by switching from reals to a finite field, we will not lose anything, which is always nice. So here are some more elliptic curves, because I think I get paid by how many elliptic curves I show you. So here are some more. And you can see how the change in the coefficient vary the shape of the curve, which I think is quite nice visualization. Here is some other ones, and in particular here I want to draw a distinction. So the top three are what we call non-singular curves, which also means essentially in mathematician jargon just means nice, while the one on the bottom, they're singular curves, which essentially just means they're not nice. What makes them not nice is that there are some points, these two, like at 0, 0, in which the tangent from the elliptic curve is not well defined. All the other points, all the other curves, like all their points have a unique tangent. In this case, the tangent is, there are two tangents which you can consider. And when you're looking about the addition formulas, tangent is something which are very important to us. So we want to find an easy criteria to discard this kind of curves. And what we're finding is that discriminate between the singular and the non-singular curve is something which is very imaginatively named the discriminant. So numerically, the discriminant is given by that formula there, which I'm not going to try to read. And a curve is singular if and only if this discriminant is equal to 0. So all the curves that we'll be looking at, which are nice, will have a discriminant which is not 0. That formula there is a bit obscure. Is not exactly clear where it comes from, but something which can illuminate us is that we can take our Weierstrass equation and look at the roots of the polynomial in X. And in fact, if you do the algebra, it turns out that the discriminant is exactly equal to this polynomial in the roots, which essentially is 0 if and only if the f has got some repeated roots. And this is a way that we can reason about the discriminant. Essentially, the discriminant tells you whether the f has got repeated roots or not. Cool. From now on, we will have that all the curves that we will going to be looking at will be assumed non-singular, which in fact is what we will see almost everywhere. Like elliptic curves are assumed non-singular because in the singular case, most things just break. And in fact, we will see later on that something like, for example, the discrete logarithm is much easier to solve on singular curves. So another quantity we're going to be looking at, which is very important, especially when we're looking for supersingular isogeny graphs and post-quantum schemes, is the j-invariant. So the way that you can think about the j-invariant is that it is kind of a tag which you can give to curves. It is easy to compute. You can just if you have two curves, you can compute the j-invariant very efficiently, and if the j-invariant will be the same if and only if the two curves are really the same. They might look a bit different, but they're the same. Mathematically, that kind of concept is what's called an isomorphism. So if two curves look the same or are effectively the same, they will be isomorphic. In fact, we can characterize this kind of isomorphism of being something of this kind of form, like will be a map that takes a point in the curve and just essentially scales it by either the square of the cube of this element q. And in fact, you can prove what I was talking about before, that if two curves have the same j-invariant, then they are isomorphic, and if two curves are isomorphic, then they have the same j-invariant. This is something which is not true for a lot of other structures, and this is a very desirable property. For example, if you think about graphs, the problem of deciding whether two graphs are isomorphic is something which is computationally very hard. With elliptic curves, it is very easy. You just have to compute the j-invariant of the curves, which is something which is very easy to do. And if it is the same, then you'll know that the curves are isomorphic. And in fact, you can also find the isomorphism quite easily from there. So this is something which is quite nice about elliptic curves, one of the many things which is nice. Okay, I've been teasing you a little bit about what the group law is for a while, and now we can look at it. Essentially, this is the way that we're going to get the elliptic curve, which is a geometric object, mind you, and then give it an algebraic structure. So the main idea of the group law is that we want to make sure. So we start by thinking about the intersection of a line with the curve. Since the line has got since the line is of degree 1 and the curve is of degree 3, you will have 3 points of intersection. While the geometric thing that we want to have for this group operation is that if we have 3 points on the same line, then their sum will be 0. Well, will be the identity of the group, which in our case will be infinity. So why do we need infinity? Well, consider, for example, this point P and the point directly opposite of it, right? Exactly perpendicular. This will only intersect the curve in 2 points, right? Well, technically not, because they also intersect the curve at infinity. So that's kind of the idea that we want to have. So these points at infinity that we talked about before allows us to make sure that the curve is always have exactly 3 points, counting multiplicities, which we'll see later what that means. Okay, so what we're going to be doing is applying this criteria. We're going to be making the infinity our identity of this group. So this suggests that from the point P, the inverse of P will be the point exactly on the other side, because if we connect them, then the other point on the line will be infinity. Okay. If we have instead 2 more traditional points like P and Q, we simply, to compute P plus Q, we simply take the line to of it, and then take the negation of it. This essentially ensures that if you take P, so the point on the line will be the negation of the sum of the other 2. So if we do P plus Q minus P plus Q, then you will get 0, which is the point at infinity, which is what we want. So this is the main idea between the group law formula. Okay, we've seen this geometrically. Now we're going to be moving it to something that then we can translate to the finite field. So we're going to take one elliptic curve in short Weiss transform, and then we're going to be taking like some points. We'll take 3 points of it for convenience. So for negation, we're going to be saying what I was saying before. We flip around the x-axis. So if the point pi is at 0 and y 0, its negation will be at 0 and minus y 0. Now we're going to be looking at some, and these are things that are a bit not as nice. This is the reason why some of the other models which I was talking before, such as Edward curves and Montgomery curves, are sometimes a bit nicer, but we'll manage. So there are some few cases that we want to handle. First of all, if the other point, so is the negation of the other, so right, if the x coordinate is the same and the y coordinate is the negation, then we know that P1, that P2 is equal to minus P1, so their sum should be infinity. Secondly, if P1 is equal to infinity or P2 is equal to infinity, then we just return the other point because we want infinity to act like the identity. Okay, so these are all the uninteresting cases, and now we can look at the interesting one. So it's a bit of algebra, but we calculate this delta, sorry, this lambda, which if the points are different, then will just be the line connecting the 2 points, right? This is just the equation of the line connecting the 2 points. If instead we have that P1 is actually equal to P2, then this is a case that we haven't talked about before. And we go back. In the case, what it makes sense is to consider the tangent of the line at that point and then find its intersection of the point. You might say, well, but doesn't that only intersect the curve two times? Well, that's what I was saying up to multiplicities, because we consider the tangent as a point of multiplicity 2, so actually we still have free intersection with the line. It's a bit cheating, but we'll allow it. I mean, allow it, I make the rules. Well, they made the rules some time back, I don't know who. But anyways, okay, and you can look at this, that this is just simply the coefficient of the tangent of the point. Okay, cool. Then from that tangent we can find out the net intersection with the line and then flip it, and we can get these formulas to find out the net points, and that is what gives us the group law. And you can check that these satisfy all the what we need for a group. So we will have that infinity is an identity. We will have that every element has got an inverse, and we will have that. We will have that. The only thing that we are missing is associativity, which is not as easy to prove, but you can verify it either algebraically or you can verify it geometrically. It's a bit more complex, but we'll just assume that it works because we know that it does. So you can find out a proof for associativity, but it just becomes quite a bit of a mess, so we will not. Okay, cool. Next we're going to be looking at something which is called scalar multiplication. So a scalar multiplication is essentially what happens when you take a point and you add it to itself a lot of times. And it is what will be the basis for our Diffie-Hellman based schemes later on. So this is just this is a notation which I've taken from Silverman, which I think is quite nice because later we'll see the multiplication by m very soon. We'll see the multiplication by m endomorphism, and this suggests that the scalar multiplication and that endomorphism are kind of the same thing, which they are. So I like this notation. And something which is important is that scalar multiplication can be computed very efficiently. If you can imagine n being a very big number, right? Imagine 2 to the L, and in fact, if you were doing it naively, it would be very, very slow to compute the sum of like 2 to the L sums. But in fact, we can use an algorithm which is called double and add to actually do it in logarithmic time. So this is much more efficient, and it is it's something which you can do in a lot of different groups. You can do it for a lot of generic structure, but it's something which enables us to then set up the difficulty of the discrete logarithm problem. Because if it were hard to compute discrete logarithm, to compute scalar multiplication, it would make all our it would make our cryptography much more difficult to do. Okay, we also define this map here, which is called the multiplication by M endomorphism. Endomorphism just means that both its source and target are the same thing, because endo means into itself. This is defined exactly as you might do. So it takes a point and it just simply raises to the does scalar multiplication with M. We also write this distinguisher, which is called the M torsion subgroup of E, which is essentially all the points which are sent to infinity by this map here. So, for example, you might think if you have a point on the curve of order 2, then it will be in the 2 torsion. If you have a point of order 6, it will be in both the 2 torsion, the 3 torsion, and the 6 torsion. So, essentially, we are interested in them because points of finite order are mostly the only one that we are interested on, because we're going to be looking at the finite case mostly. Okay. For cryptography, it is very important to know how many points are on a curve. And we can already do some kind of estimates of that. So you can essentially see that every value of x can at most give you 2 values of y. So it essentially gives you an upper bound of 2q plus 1, where the plus 1 comes from the fact that we also need to count the point at infinity. In fact, if you know a bit of number theory, you also know that a random element has got exactly a 50% chance of being a quadratic residue. So essentially what this means is that we should expect around q plus 1 points to be on a curve. And in fact, we are very close. There's a theorem by Hasse, which essentially says that this naive estimate is within 2 square roots of the actual right result. And in fact, we can efficiently find out what the correct number is by using Schuf's algorithm, which is very elegant, which does it in polylogarithmic time, which is quite nice. All right, now we can take a brief excursus into cryptography. So cryptographers and computer scientists in general, they are ended a very short stick, because cryptographers in particular, they need to prove that things are hard to do. And that is something which is in general very hard to do, ironically, I would say. Because for a fundamental reason, showing that something is easy to do or something that has a solution can be done by just exhibiting the solution. Sure, finding a solution might be very, very hard, but it can be done. If instead we have to show that no solution exists, that is something which is much harder, because you essentially have to consider all the possibilities and prove that they give you a contradiction. And especially when we're talking about algorithm, that is something that we are just not good at doing. This is in a sense, is very similar to the NP versus the co-NP problem, right? NP are solutions, are problems which can be efficiently verified that they have a solution. Whose solution can be efficiently verified, while co-NP, there are problems in which you essentially have to show that no solution exists. And that's and we consider co-NP to be harder than NP generally. I mean, but it's so essentially it is very hard to do. There are some models of computation in which you can distinguish, like we can give lower bounds. For example, decision trees, you can give lower bounds of complexity. In computational complexity models, you can also give lower bounds. But in general, that is something that we're not able to do. So how do we, as cryptographers, go over this hurdle and have confidence that our constructions are secure? Well, essentially, you build what I call a tower of problems. You start by taking some problem which nobody has found a solution for. So, for example, you take a problem which is hard, which we only know exponential algorithms or sub-exponential algorithms for computation. and then you build onto it. You build schemes that you like, that you know that breaking those schemes will also break the original problem that it was based on. Essentially, by building these layers of abstractions, as long as the underlying problem is secure, then you're able to show that the construction that you have is secure. So that's kind of like a bit of the overview of why we need hardness assumptions. And in particular, one of the ones which we rely most heavily is the discrete logarithm assumption. This is something which is fundamentally very similar to taking the logarithm in the reals, right? If you have a number like 256, you want to take a logarithm base 2, then you can simply do it. You'll be what, 2 to the 8 is 256, so the logarithm will be 8. So in the reals, you can do that very easily. You can approximate it. Even in the rationals, you can do it quite easily. Even in the integers, if the logarithm exists, you can do it. In finite fields, that is very much harder, and that's something which has eluded a solution for a long time. So since we don't know of an algorithm which solves it better than essentially the generic methods, which are exponential, we believe that the discrete logarithm is hard. And so we can make an assumption out of it, which is the discrete logarithm assumption. So don't get too scared about this. This is essentially how we can state this. Essentially, we define what's called, we take an algorithm which generates groups. And we are interested in particular in asymptotic complexity. So we would like to know, okay, if the problem becomes harder, like so for example the keys become bigger or something like that, how does the difficulty of the problem behave? So we formalize this by using a group generation algorithm, which is an algorithm which just takes a security parameter and generates a group. In our case, a cyclic group of order q. And then we define the advantage of an algorithm with regards to this group. So the adversary will be given the scalar multiplication of this point, which is known to him, with a value that we select at random. And we want to figure out how good this adversary is at finding that value k. Our wager is that no attacker, which is probabilistic polynomial time, will be able to do particularly well at it. We would say that their advantage is negligible. And the discrete logarithm assumption essentially says that, look, we think that for any possible attacker, nobody will be able to win this game more than negligibly. And essentially, this says that the probability of success decreases in a kind of exponential manner, which is good enough for us. So that's the kind of thing that the discrete logarithm assumption allows us. And in fact, the discrete logarithm assumption is quite a weak assumption in the sense that we cannot really use it to prove anything interesting. So in practice, we have to make stronger assumptions, which are the computational Diffie-Hellman and the decision Diffie-Hellman, which are so called because they have a lot to do with the Diffie-Hellman case change that we will see later on. So the computational Diffie-Hellman essentially tells you that from the scalar multiplication of 2 points, you can compute a point which is the scalar multiple of which is the scalar multiple of the other two, right? So you can see that knowing x and knowing yp will allow you to get xyp and vice versa. So, and we'll see later that it is exactly how you do Diffie-Hellman. So that's why it's called the computational Diffie-Hellman problem. The other problem that we have is the decisional Diffie-Hellman problem. So while the DLP and the CDH were purely computational problem, DDH is a decisional problem. So he asks us to distinguish between two kinds of pairs. So there are those which are called the genuine Diffie-Hellman quadruples in this case, which essentially have the same form as we've seen before. And then we have the ones which have a random scalar multiples. And the assumption is that for an attacker it will be hard to figure out in which of the two cases it is. So using these two assumptions are essentially the workhorse of a lot of our cryptography. And in fact, it's quite interesting because in elliptic curves, we know that the decisional Diffie-Hellman problem is actually quite easy, since we can use what we'll see later on, the pairings, to efficiently verify whether we are in the first case or in the second case. While we think that the computational Diffie-Hellman problem, it is still hard on the elliptic curves. In particular, this is the hierarchy of hardness. So we have that DLP is the hardest problem, because if you know DLP, then you can solve computational Diffie-Hellman, you can solve DDH by simply taking the discrete log. We think that the computational Diffie-Hellman is harder than the decisional Diffie-Hellman, because you can, if you can compute, then you can just simply verify whether this value here is the same as this two here, as the multiplication of these two here. And exactly, so this is the hierarchy problem. And in fact, we know that the computational Diffie-Hellman problem and the discrete logarithm problems are equivalent in some groups, but it's a result which is by no means obvious. Something else which I want to mention is that representation matters quite a lot. Two groups can be isomorphic to each other, and in fact they will be, since we're only looking at cyclic groups at the moment. But the discrete logarithm problem can be much easier in one than in the other. So, for example, if you take the integers modulo p minus 1 using additions as the group operations, then it is very, very easy to take discrete logarithms. If instead you look at the multiplicative group modulo p, which has the same order, so they're isomorphic because they're both cyclic, then the discrete logarithm in that group is quite hard, which is quite interesting, because that means that essentially means that hardness is not invariant under isomorphism. So the next question that you might have is like, look, why do we need elliptic curves? There are a lot of other cryptographic things. Why do we need this very complicated algebraic geometry thing instead of maybe using RSA, which is, conceptually much easier? Well, and that the reason relies mostly in the attacks which are available against these kind of primitives. So here we have three cases. We have RSA. We have the discrete logarithm in the multiplicative group of a finite field, and we have the discrete logarithm in elliptic curves. And in both of the two previous cases, the best attacks are those by the number field sieves, and the complexity of these attacks is the sub-exponentials. In contrast, the best known attacks against ECC is the Pollard Rho method, which we'll see a bit about it later on, which has got an exponential complexity. So what does this mean? Well, essentially that means that when you're trying to make a scheme, you essentially want to provide a certain amount of security, which is called bit security, which what it amounts to is saying that the best attack known against this primitive must take at least 2 to the 128 step of complexity, which are not better defined. If the complexity of the attack is exponential instead of super exponential, that means that you can get away with smaller and more efficient keys, and that has got like a lot of very good benefits. So, for example, the shorter key sizes. In elliptic curves, you can get away with 256 bits keys, while for RSA and the discrete logarithm, you need keys which are around 372 bits. So that's a very big saving in space. In some cases, this is not true all the time. You also can get faster computation. In particular, RSA has got faster public key computation than the discrete logarithm problem, but the discrete logarithm has got faster private computation than RSA, because it is computing in a smaller field. So the P and the N are smaller. So those are very good benefit, especially if you're doing something like TLS, which is working over the wire and in which communication costs might be non-trivial. Or even if you're doing like something which is on, for example, hardware constrained device where you might have a little memory, it is a very, very big benefit. Okay, now let us look at the Diffie-Hellman key exchange, which you might have seen before. So we essentially take an elliptic curve over a finite field of order Q, and we take some large prime dividing the number of points on the curve, and we take a point of that order on the curve. So the way that the Diffie-Hellman key exchange works is that both Alice and Bob select a secret exponent, and then they do scalar multiplication of the secret exponent and send it to the other party. Once they receive the other's exponent, they simply do another scalar multiplication with their private key, and that allows you to get to the same point. And the correctness follows simply by taking this by property of the commutativity. So you can essentially swap the order of the scalar multiplication. So this is a very simple scheme which allows you to do a lot of very cool stuff. For example, you can make it a bit more complicated. You can do what the signal does, which is essentially a triple Diffie-Hellman exchange, which allows you to have some different security property. You can make it, you can have forward secrecy, which essentially means that even if the long-term keys are exposed, you still maintain your privacy in the future. So it has a lot of very, very cool properties. But something that you have to be aware of is that the discrete logarithm problem is not equally hard on every curve. And this is something which often is not mentioned, but you want to choose curves which have got, which are tested and they are known to be secure, or well, that they are believed to be secure. And there's a bit of controversy over this. For example, I personally kind of like the NIST curves, but there has been some controversy in the way that they were generated, and there has been the suspicion that they actually were backdoored by the NSA. I don't think that happened, but it is a reason why some people decide to go for other curves. But it's something which I wanted to mention historically. But anyway, so the discrete logarithm, there are some curves in which the DLP is easy. So as I said before, singular curves are one of these. Singular curves essentially they behave badly because you can compute a very efficient isomorphism from the group of points on the elliptic curve to a finite field of the same size. Either the multiplicative group, which is best case, or the additive group, which is very, very, very easy to solve. So essentially what that means is that you can move it to a field which is much easier to solve. So we saw before that to get 256 bits of security in a finite field, you need around to get 128 bits of security in finite field, you need around 372 bits. So solving the discrete logarithm problem in a finite field of size around 256 by this, which is what we get by this method, is something which is much easier to do. So you lose a lot of security by using a singular curve. So that's one reason why you should never ever use a singular curve. Next, there is this embedding degree. Essentially, every curve has got something which is called an embedding degree, and you can essentially there's an algorithm which is called the move algorithm, which can take a discrete logarithm in the elliptic curve and then move it to a finite field of order p to the embedding degree. If the embedding degree is small, which most often is not, then you will be able to solve the discrete logarithm in that finite field, and that is game over, because you get you can reduce the security of the curve considerably. For example, supersingular curves and anomalous curves have usually very small embedding degrees. So in those curves, the discrete logarithm is easier. Also, pairings allow you to break the discrete logarithm. So if you have a curve which admits pairing to some small finite fields, essentially the same attack apply. But we'll see later about pairings what they are. Finally, there are some curves which are a bit more. It is an attack which are there are some attacks which are a lot more complicated. But if you have a curve defined over fp to the k, where k has got a lot of small factors, then there are the GHS method and DMS analysis. They give you sub-exponential attacks, which of course they're not very good to have against your curve because they reduce your security considerably. Of course, this is not meant to be a complete list, so please do not choose your own parameters unless you know what you're doing, because otherwise you might get your lunch stolen, which is always not nice. Okay, let us now look at like some methods for finding discrete logarithms, and the one that we're going to be looking at is called Pollard Rho. And it's called Pollard Rho because we'll see it traces a row and it was invented by Pollard. So essentially, this is a collision search method, which is general for almost every function, which is an end of function. So it's got the same domain and codomain. So the idea of the method is that you can start from you take a point in your domain, and then you just keep iterating the function, looking for a collision. And the cost of this attack is approximately square root of the size of the set. And in fact, this is an improvement over other methods such as the big stack giant step method, because it has constant memory. And it's called the Pollard Rho method because it looks like a row. The main idea is that you keep walking over this by iterating the function, and at some point you will end up in a loop. And once you enter into the loop, you can walk and find a collision. The way this is done in practice is they usually have two iterators. One which step by one function call at any point, and one which does two at any point. So essentially, these are sometimes called the hare and tortoise method, because essentially what happens is that one iterator traverses the loop slowly, while an iterator traverses it much quicker. So at some point, the two iterators will get to the same point, and then you will have you will be able to find a collision in constant memory. So it's a very nice method to talk about because it's very easy to explain. The analysis is not too hard to do. In practice, there are better methods that you can use for this collision search, such as the Van Oshot and Wiener method, which essentially improves on this by being parallelizable, while making a trade-off that it uses quite a bit more memory. But we will see that later for when we want to break isogenies. Okay, how can we? Okay, so we have this Pollard Rho method. Now we just need to find out a function which is good enough for finding collision. So the two properties that we want them to have is what's called rapid mixing. So essentially, it means that it will take element of the group and just move them in a kind of pseudo-random manner, and it must be easy to compute and to track exponents. So Pollard proposed the following one. So you take your group and then you split it into three sets which have approximately the same size. We want to find a discrete logarithm of q to base p. Then the function will be defined as follows. You take the point x, and then you look in which of the three classes this falls down. And depending on that, you either sum the base, you sum the exponent, or you do a scalar multiplication. So the way that we can solve is that we can start from the point at infinity, and then you can keep iterating, keeping track of these coefficients, which you can always do, because if you if you take a step in the function, you can always keep track of these points. If you get to a collision with this property, essentially, which allows us to compute an inverse, then you can find k modulo n by these very simple calculations. And in fact, most of the time we're going to be concerned with g being prime, and so the order being prime, and so this will be true very, very often. So if you find a collision, you're very, very much likely to be able to break the discrete logarithm, and you don't have to start again. So that's kind of the gist of Pollard method, which yeah, I think is a quite nice method. Okay. All right, next up we'll look at pairings. So a pairing is a map from which takes in two groups elements and spits out a third one of possibly a different group. So first of all, a word on notion. We have some properties which to satisfy, but the first thing which I want to notice is that with pairing we write the operation on the base groups additively, but traditionally the group in which we're going into is multiplicative. So in this case, the identity for the group is 1 and not 0. Okay, so the property that we want from a pairing, first of all, it is non-degeneracy. Essentially, a pairing is degenerate if it is the one map, so the map which maps every element to 1. We want to make sure that that does not happen, so that's one of the, otherwise it will be very trivial to have a pairing. Okay, so we want non-degeneracy. The next property, which is possibly the most interesting one, is bilinearity. That essentially means that if you have a sum in the first argument, then you have a product of pairings. And if you have a sum in the second argument, you also have the product of the pairing. This is quite important, especially because you will see later, you can essentially combine these things. So this allows you essentially, if you have here a scalar multiplication, you're able to bring the exponent to the other argument, which is very convenient, or even outside of the pairing. And that's also the reason why pairings can be used to break the discrete log, because if you can get a pairing to a field of a small order, then you're able to solve the discrete log there, and essentially allows you to solve the discrete log in the actual in the original group. So yeah, essentially, if you have a group with a pairing to a small field or to a small group, then the discrete logarithm in the original group would have been easy. The other property is that the pairing is alternating. So if the two arguments are the same, then it is 1. Now I'm gonna just go on a little bit of a brief excursus. This is not exactly the standard definition. The standard definition is a bit more general than that, so it allows for G and these two groups to actually be different, so to have two different groups. And also they usually tack on alternating as an extra property. But since all the pairings that we're going to be seeing are alternating anyways, then we might as well add it to the definition. Okay, elliptic groups are particular because they admit this pairing, which is called the while pairing. Essentially, the while pairing is a pairing which takes two arguments from the torsion group of the curve, and then outputs an element of UM, where UM is the group of M for unity over the base field. So the exact details of how it is done, they're a bit more obscure, but we don't really need to know them. We just need to know that this is a pairing which is efficiently computable, and we can use that for our construction later on. In particular, though, this is not exactly as good as we want, because we would like to have a pairing which is non-degenerate on cyclic subgroups of the torsion group. That is because in cryptographic application, typically we take a point of a large prime order, and then we work in a cyclic subgroup generated by it. But unfortunately, the standard while pairing is actually degenerate on those subgroups. So what we need to do is to modify it, and we use what's called the modified will pairing, which I think The first time I seen it was in Bonnet's paper, but I might be wrong. Essentially what we do, we take this thing which is a distortion map, which not every curve has one of them, but if you have the one, you can do this modified well pairing, so you can then do the construction that we'll see later on. And you just take the original well pairing and simply apply this distortion map to the second argument or the first argument, it doesn't really matter. And essentially this distortion map makes so that the pairing is non-degenerate on the cyclic subgroups and all the other properties are preserved. So we get an alternating non-degenerate multilinear pairing from the cyclic subgroups of the torsion, which is what we're going to need for what we're going to be seeing next. So these are what we're going to be seeing are the BLS signatures, which essentially they are very efficient signatures, which also have the property that they are aggregatable. So essentially you can aggregate signatures and then verify them all at once, which is always quite nice. So we're going to get a bit of ingredients. So we're going to get, I'm going to do the general case with not on the elliptic curve, but you can just simply replace the instantiation. So essentially you start getting some cyclic groups of order P, a generator, and a non-degenerate pairing according to the definition that we saw before. We're also going to need a Nash function which maps to element of the group. This might be sounding a bit daunting, but in fact there is an algorithm which is called hash to curve, which allows you to take, which is a Nash function which maps to element of an elliptic curve. So in practice we can do that quite efficiently as well. Okay, the key generation is very simple. It is essentially the same as a Diffie element generation. So we generate a scalar x. The public key is the scalar multiplication of x with the base point, and the secret key is just that point. So nothing weird there. For signing a message, we use the hash function to map it to a point to a curve. Then we take the scalar multiplication with the secret to get the signature. Where the magic is in the verification. In the verification, we just verify this pairing equation, and you can see by using the property of the pairing that this will be correct, and in fact this will actually be secure as well, assuming of course the hardness of inverting the pairing and all the discrete logarithm problems and all this kind of stuff. So that's how you do BLS signatures, which are very cool tool. Especially right now they're getting a lot of usage as well in blockchain, since the probability of the possibility of being aggregatable allows verification to be much more efficient. Cool. With that, we have finished our excursus into classical cryptography with elliptic curves, and we can move on to the post-quantum stuff. So first of all, you might have already heard I mentioned in the introduction that a lot of our public key crypto is broken by Shor's algorithm or things which are related to Shor's algorithm. And this is in fact true. Discrete logarithm, RSA, and pairings, they're all broken by the Shor's algorithm. In fact, elliptic curves are broken more efficiently by Shor's algorithm than RSA is, which is which is not good news for us. But of course, we still wanna continue to do cryptography. And the answer to this challenge is it's been a development of what's called post-quantum cryptography. So the question is, can we recover? And the answer is yes. There are some methods that we believe are secure even against quantum attackers. For example, there are lattices, there are codes, there are multilinear maps. All of them are very interesting mathematically, but it's a bit unsatisfying, right? Because we have a lot of theory on elliptic curves. They're a very interesting tool. They usually allow you to have a very short keys, almost counterintuitively short. We would like to keep using them as much as possible. We can also benefit of implementation of multiplication and other things which have been done beforehand. So is there a way that we can recover? Yes, isogenies. So I might have spoiled you before in introduction, but isogenies, they allow you to actually do post-quantum secure cryptography using elliptic curves, which is very nice. But first of all, what is an isogeny? Well, an isogeny is the equivalent of a nice map between elliptic curve. So you might have done a bit of category theory or not, but when we are looking at mathematical objects, we tend to look at two things in particular. We tend to look at the object itself, and most importantly, depending on which view you have, we look at the maps between these kind of objects, and we want to select some maps which have some properties which allow you to, which essentially they behave nicely with the property of the objects. And isogeny, they do that for elliptic curves. We've seen that elliptic curves, they have both a geometric nature and algebraic nature. So isogenies, ideally, they would have to behave well with regards to both, and that's exactly what they do. So the definition is of an isogeny is simply a morphism. So morphism is in the sense of morphism of algebraic geometry, and essentially it is you can think about it as a polynomial map. So it's a map that takes a point which is made of the component x and y, and then turns it into and then maps it to another 2 points x and y where the coordinates are polynomial. And we also require that the infinity point, so the identity of the group is mapped to the identity of the group of the second curve, which is which we need. If there is an isogeny between two curves, then we call them isogenous, unsurprisingly. So this is an example of an isogeny. This is these are two curves over F71, and this is an isogeny which maps one to the other. It's very complicated, but this is an isogeny between them. That's how it looks. So you have essentially two polynomials in x and y, and in fact we will see that each isogeny is also a group of homomorphisms. So isogenies, they are exactly the map that we need. They are geometrically nice, so because they're polynomials, and they also are a group of homomorphisms. So we have already seen some isogeny. For example, the multiplication by m endomorphism is an isogeny, because essentially you can unwind the multiplication. We see that the scalar multiplication map is essentially a polynomial, and so if you compose it a lot of times, then you get a very big polynomial, but a polynomial nonetheless. And it maps infinity to infinity, of course, because if you have infinity and you raise it to any scalar multiple, it will still be infinity. Isogenies, they behave nicely, so you can compose to isogeny and get an isogeny, which is what, the minimum requirement for a category, which is something which we like. They also have this feature of having a degree. Essentially, the degree measures how complex the isogeny is in terms of the polynomial, or it can be defined in a couple of other ways. For example, it is also the size of the kernel, and it is a multiplicative. So if the degree of a composition of an isogeny of two isogenies is the multiplication of the degrees, which is something which we like. Furthermore, each isogeny also has a dual. So if you have an isogeny from one curve to another, there will be a unique isogeny from that other curve to the first one, such that the composition of the two will be the multiplication by the degree of the isogeny, which is very, very nice. And we'll see later when we're working with the supersingular isogeny graph that this essentially allows us to have a directed graph rather than an undirected graph rather than a directed one. We also can characterize the form of isogenies between Weierstrass form, and essentially they will have a polynomial numerator, and then they will have a denominator which is a square in the y and a cube on the a square in the x and a cube in the y's. So those are the kind of forms. With those properties out of the way, let's move towards the separable and inseparable isogenies. So we're gonna start by defining this very important isogeny, which is called the Frobenius. Essentially, it is the isogeny which simply take the pair x and y and raises to a power of the prime, which is the characteristic of the field. So in particular, we can take first of all we can take any curve over a field of characteristic p, and then define some curve which is exactly the same as the original one, but with the coefficients to the power of p to some r. And the map, which essentially mapped from the original curve to this one by simply raising x and y, is called the Frobenius isogeny. This map is very important for a number of reasons, and I don't really want to go too much into it, but the reason that it is important for us is because we need to know about it to exclude it from a theorem that we're going to be looking next. So in particular, if k is equal to this to the final field on p to the r element, then these two curves are actually the same, and then the Frobenius becomes an endomorphism. So we're going to classify isogenies by how they interact with the Frobenius. If an isogeny is an isogeny plus the Frobenius, then we call it an inseparable isogeny. If it is a Frobenius plus an isomorphism, then we call it purely inseparable. And in fact, for our cases, we'll be looking at the separable case mostly, in particular for the next thing. But these are quite interesting. The Frobenius has got like a lot of uses. For example, I think even if you're looking at the Schurz algorithm, uses the Frobenius to actually estimate the number of points. I think, or the trace of the Frobenius. So why we needed to exclude it is because of this theorem which essentially says that if you have a finite subgroup of the elliptic curve, you can find an isogeny from that curve, which is separable, and there is a one-to-one correspondence between the two, up to, of course, post-composition with isomorphism. Because if you take, if you take an isogeny and then you add an isomorphism to the end, it will still be a separable isogenies, and so that we have to account for that. In particular, this is even stronger than that. The correspondence is that the subgroup will become the kernel of the isogeny. So for any subgroup, we can find an isogeny which has that kernel to some curve that we don't really know about. But this is only for separable isogeny. If we include inseparable isogenies, then this theorem gets a bit messier. So that's the reason why we want this, and especially because this will be essentially the bread and butter of the supersingular isogeny Diffie-Hellman, because we're going to be sampling kernels as our keys, and then we're going to be using that to get isogenies. So here I've been a bit more precise, because the most important thing is that we can actually, given that kernel, we can actually find that isogeny in linear time in the size of the kernel by using Velu's formula. Something which is important to note is that Velu's formula, by Velu's formula you can find an isogeny from a curve with a determined kernel, but it does not give any guarantees to what the target curve is. So you can start from a curve A, you're like, okay, I want an isogeny with kernel, I don't know, p plus 3 for some p plus 3q for some p plus 3q, and then Velu's will magically split out a curve which might be very ugly, very bad, but with that kernel. So that's the thing. So essentially, Velu's give you both the curve on which it lands on and the isogeny, which is important for us. Velu's formulas are very important, but as they're a bit too slow for a large degree. Because if we were wanting to, for example, compute an isogeny of size 2 to the L, for example, then it would be linear in that size, so it would take 2 to the L steps, which is too much. What we do is something which is similar to the add and multiply. Sorry, to the double and add algorithm. Essentially, we decompose this sequence of L to the k isogeny into k L isogenies. And this essentially gives you a speed up from a time which was exponential in k to something which is just quadratic in k, which is a very, very good improvement. In particular, this is how we do it. So if we have a kernel, then we build a sequence of isogenies, each of degree L, and then the composition out of all of them will be an isogeny of degree L to the k, because the degree is multiplicative, and it will have the desired kernel. So, and that's how we do it. And that's going to be the way that later on we're going to be stepping efficiently in the supersingular graph. So I've said supersingular a couple of times. What does that mean? Well, there are a lot of equivalent ways of defining supersingular curves, and here I've went for the one that we could do with the theory that we have seen so far. So a curve is supersingular if the multiplication by p map is purely inseparable, so it is the Frobenius plus an isomorphism, and if it's j-invariant, is in the finite field of order p squared. If we have a curve that is not supersingular, it is ordinary. So first, a little note on why they are called supersingular. We've seen before that the singular curves were something which were bad, and are supersingular curves super bad? No, it really this is actually a bit of a misnomer. Essentially, what happens is that the curves which are supersingular, they have what's called complex multiplication, which is something which like normal curves do not have. So the normal curves are ordinary. These curves with these particular properties, they're called supersingular because they're like kind of weird, but they are not singular. They're actually a supersingular curve is non-singular. It's something important. So I think the most important characterization of a supersingularity is it has to do with the endomorphism ring. I don't want to go too much into it because I think it deviates a bit from what we're doing, but essentially you can look at the ring of all isogenies of all endomorphisms, so isogenies from the curve to itself, and look at that how that behaves. And it turns out that if you have a supersingular curve, then this endomorphism ring is an order in a quaternion algebra, and that is very important, especially in light of something called the Turing correspondence. But we will not touch on that particularly right now. Just something which is important to mention in case you want to go and learn more, because this is one of the definitions of the equivalent condition for supersingularity, but it is not by any means the most interesting one. So we actually know how many supersingular curves there are over any finite field, and there are around p over 12. Is either p over 12 plus 1, p over 12 plus 2, and maybe p over 12 over plus 3, I'm not sure, depending on essentially the remainder of p modulo something. Supersingular curve also are kind of nice. They have exactly p plus 1 points, which is exactly what we... which if the curve was is over fq is exactly what we expected for our heuristic. We have seen before though that supersingular curves are insecure for the discrete logarithm problem, but surprisingly they're actually secure for the computational supersingular isogeny problem, which is what we're going to be seeing next. And this is quite interesting because in a post-quantum world the difficulty is swapped. So for example, you can do some of the construction we've seen before with ordinary curves, but then there are actually more efficient algorithms for breaking them. So we really need the supersingular curve in order to have security. But we'll see now what the computational problem that isogenies have is. So the first thing is that it is as we've seen before, it is very easy to find out whether two curves are isomorphic by just computing the j-invariant, and in fact it is also very easy to find out if two curves are isogenous. In fact, they will be isogenous if and only if they have the same number of points. So that's something, given two curves we can find out whether they are isogenous. However, finding the isogeny between the two of them is something which is dramatically hard. And in fact, that's the problem that we will be using to build our crypto systems. In particular, this is going to be the computational supersingular isogeny problem. It is as follows. If you have two supersingular isogenies, elliptic curves E and E prime, which are isogenous, to find the isogeny which connects them. And that is something which we believe very hard. The best algorithm that we have is the Van Oxford and Wiener collision search, we will see later, but that's what we're going to be building our schemes on. And in particular, we're going to be using something which are called isogeny graphs. So isogeny graphs are essentially graphs in which you have isomorphisms, class of isogenies as vertices, and as edges you have separable isogenies between them. Here are two different ones. This is the graph which has been used in SIDH, spelled S-C-I-H, spelled C-S-I-D-H, but pronounced SIDH. But we're going to be focusing mostly on this one, which is the supersingular isogeny graph for SIDH, which is a supersingular isogeny diffie-Hellman, which is the one which has been considered for instant standardization. Okay, let us go now on to define what the supersingular isogeny graphs are. So, okay, little technical thing. Okay, so essentially, as I said before, there are graphs which have as vertices, they have supersingular elliptic curves over some field. As edges, they have separable isogenies from these curves. All of these are both up to isomorphism. So, for example, if two curves have the same j-invariant, they're put in the same bucket. So we will have the vertices with j-invariants, and the isogenies with that will also be nicely clumped together. So it has some important properties. As we've seen before, that supersingular elliptic curve, they have a j-invariant, an element of fp squared. Essentially, this means that we can represent them quite efficiently. We can represent them as an element of fp squared, which is essentially just as a scalar in our case. The graph will be directed by virtue of the dual isogeny. So if you go from one curve to another, you'll also be able to go back by just computing the dual. One of the most important properties of this graph is that it has got good mixing properties. This is a property which is also sometimes called being Ramanujan. Essentially, what it means is that if you take a random walk in the graph, but even by taking few steps, you will be able to get to something which resembles a uniform distribution on the graph. So it's almost like selecting a point at random, which is something very good, because we will see afterwards that the SIDH problems essentially is about walking at random in the supersingular isogeny graph. And this walk can be done by Velu's method. Essentially, this graph has got, as edges, it's got separable isogenies of degree L. So a step in this graph is one application of Velu's method. And this graph is also will be regular, with most vertices have degree L plus 1. Of course, out to multiplicities, there are a couple of curves which are weird, and they are a negligible set. Okay, so let us look at what SIDH does. So SIDH is the supersingular graph for p is equal to 431. The supersingular isogeny diffie-Hellman essentially starts by selecting a star curve. In this case, is 87i plus 190. This is the j-invariant, and then it does a walk. In this case, this is the two isogeny graph. So we're gonna start and we're gonna do 4 steps in the graph, because it is the exponent. So we do 4 steps in the graph and we get to this curve around here. This is Alice's public key. Alice will publish as public key the j-invariant on which it has landed. Bob will do essentially the same, only that he will do it in the 3 isogeny graph, and he will take 3 steps into the 4. We'll see later a bit more why this is done. So, and he will land on this curve here, 344i plus 190. Next, we're gonna be Alice will compute the public key. So we'll start from the curve from which Bob has ended, and then essentially compute this path, which is essentially a version of the path that you had computed before. We'll see later exactly how it is, but it will essentially do a path which is the same one which it had done beforehand. Bob will do the same. He'll start from from the curve where Alice landed, and then he will do a free path again. And you see that both ended on the curve with curves with j-invariant 1 and 34. So the picture to keep in mind is that you both start from the same curve, you both compute an isogeny, and then you start from the curve of the other, and then you compute a particular isogeny which lets you end on the same place. In this diagram, Alice is computing these two isogenies and Bob is computing the downwards one. Okay, it's a bit complicated, but let's see how this actually works in practice. So we start by selecting a prime which has got a particular form. In particular, it will be the product of the prime plus 1 will be a power of 2 times the power of 3. And in particular, we want to choose these exponents so that 2 to the EA and 3 to the EB are approximately of the same size. We also select a supersingular starting curve over fp squared, and 4 points. 2 of them will be on the 2e to the a torsion, and 2 of them will be to the 3 to the eb torsion. The way that it will work is that Alice and Bob will both sample a short secret. In this case, an element of for Alice will select an element from 0 to 2 to the EA, and Bob will select an element from 0 to 3 to the EB. And they will compute this secret point, which is p to the x plus the scalar multiplication of the other point. In this case, I'm using x to just save a bit of space. Alice will then compute the 2 to the EA isogeny, which has got as kernel the subgroup generated by our secret point, and we'll call this curve EA. Bob will do the same thing with EB. As public keys, they will both publish the curve in which they landed on, and this additional information, which are called the torsion point, which essentially are the images of the original point that they had over their secret isogeny. This is a bit controversial, like it's something which we need to do because otherwise we won't be able to essentially compose the isogeny in the correct way. So to compute to do the secret computation, then Alice will take the torsion point of Bob and use their secret to compute another SA and then compute an isogeny on it. Bob will do the same and land on these two, on this other curve. And in fact, it turns out that the curve on which they land on is actually, they actually have the same j-invariant, so they're isomorphic. So at the end, they both will have landed on the correct curve, and they will have a shared secret which they can figure out. And if an attacker from their public point information cannot recover their secret isogeny, and as such they cannot recover their the secret. So that's kind of the base of SIDH. It is not perfect. There are some issues with SIDH. For example, you cannot use a naive SIDH to do non-interactive case changes because there's an active attack, which essentially what it does is selects those points in a particular way such that the failure of the protocol gives away the parity of the secret. And essentially, if you can repeat that, you can essentially get the manage to extract the secret. So to fix that, SIDH, which is a supersingular isogeny key exchange, uses what's called the Fujitake-Okamoto transform, which essentially which essentially what it does, it re-encrypts or re-encapsulate and check that no foul play occurred. And SIDH has been having a moderate amount of success since it appeared in the alternate candidates of the round 3 of the NIST post-quantum cryptography competition, which is a very big deal. We are currently waiting for a decision on what's going to be happening, but it seems as NIST is most likely going to standardize it in case that lattice cryptography, which is in the main candidates encodes break, because yeah. Also, SIDH has got a lot of usages, in particular from the fact that it has very short keys compared to a lot of the other post-quantum primitives. Drawback is that it is currently a bit on the slow side compared to a lot of other things. There's a very interesting reading from Cloudflare on using SIDH and I think NTRU for TLS, and they concluded that while the short keys are very, very nice, the computation time is a bit on the slow one, so they would like to use more lattices. But yeah, that's one of the drawbacks, but it's something which will improve as more time is spent into computing isogenies and hardware. Also, another benefit of SIDH and SIDH is that the best known attack that we have is actually a classical one. SIDH and SIDH are some of the few crypto systems in which we actually think that if an attacker had enough resources to run a quantum attack, it would still be better to run the classical one with the resources that he has, which is something which makes us really awful. Of course, SIDH is a bit younger compared to a lot of the other candidates, so there's still a lot of cryptanalysis to be done, and it might be that there's actually method to compute them to break it more efficiently, even classically or quantum. But as far as we know now, it has this desirable property. And we're going to be looking at, in fact, at this best known attack, which is one on the computational supersingular isogeny problem. So suppose we wanted to find L to the A, an isogeny of degree L to the A between two curves, which are both supersingular and over sp squared. So what we can do is we can start looking at these, we can define a couple of things. So first of all, what we want to do is we're going to want to kind of meet in the middle. So we are going to be finding two isogenies of degree approximately A over 2, and essentially by a counting argument you can show that if there is an isogeny, if isogeny from one curve and one isogeny from the other of that degree in touch, that point of contact will most likely be in the original isogeny. So then you can flip one of them and get the original isogeny. So we're gonna take this set over here, which is the set of all the this is parameterized for both curves. So it takes all the subgroups of the torsion of our correct side and cyclic, which is are the ones which we use in SIDH generated, and then we take as our set on which we will then iterate. We take the disjoint union of the set from the first curve and the set from the second curve. We then define this a function which is going to be the basis of our iteration, which takes an element of this set and then computes the j-invariant of the curve. Computes an isogeny with that kernel, gets the elliptic curve, and then computes its j-invariant. In fact, you can see that if you have a collision of this form, then this will actually solve the supersingular isogeny problem. So what we want to do now is bring this into something which can use something similar to Pollard Rho to solve. In fact, what we need is that we need the function that we iterate actually maps back into S, because we've seen before that Pollard Rho needs a function which maps to the same set. And the way that you actually do that is by adding a hash function, not necessarily a cryptographic one, to the end of this function. So you first compute the G and then you hash it, and this allows you to go back in this set S. So this is not ideal, but it's the best that we can do. And the reason it is not ideal is that H will map a set which is of size around P over 12, as we've seen before, to S, which has got a size around the fourth root of P. So this introduces a lot of collisions. That essentially means that if you want to find a collision of this particular form, then we will have to find lots of collisions until we find one of these. And Pollard Rho is not ideal for this. Pollard Rho is good at finding a collision, but once it gets into that loop, it's hard to actually generate other collisions. Luckily, the Van Oshler-Wiener method is actually better for this. And we're going to use that to find what's called the golden collision. The Van Oshler-Wiener method also has the added benefit that it is very easily parallelizable. So you can essentially, it's perfectly parallelizable. I don't want to go into the details of it. I'm probably going to have a video on it soon. But essentially, you can look at the complexity of it when using M processor and W memory cells. The complexity is around the size of the set to the power of 3/2, so to the power of 1.5. Multiply where the unit of time is the cost of computing an isogeny. In particular, that means that the complexity of the attack is around p to the 3/8, which is which is the cost of the attack. And yeah, so with this, I just wanted to conclude. I think elliptic curves are a very cool topic. I think they're just an incredible amount of things to learn about it. Me myself have only scratched the surface, and in this talk we very barely scratched the surface. And I suggest you keep on going and investigating because they are very, very interesting. SIDH is the base of most WebKit exchanges, and BLS pairings and signatures are both efficient and secure, which makes elliptic curve already fundamental for our web security and our digital society. In fact, we also are able to use SIDH in order to leverage isogenies and elliptic curve for getting post-quantum security. So hopefully the future for cryptography will still remain elliptic, which something which personally I appreciate quite a bit. So I wanted to end this talk by just suggesting a couple of resources to keep researching. I've tried to give a bit of an introduction, but there's a lot of things which I've only skimmed on and which I think a more formal introduction will help. So here are some resources. There's I suggest starting from rational points on elliptic curves. Wait, let me. Yeah, I suggest to start from rational points on elliptic curves, which by Silverman and Tate, which is a very excellently written book. It deals mostly with the case where the field is actually infinite, but I think the proofs of the Mordell-Weil theorem, for example, they're very, very accessible, and it's a lot of good exercises. It's super nice. Then there's the arithmetic of elliptic curves, which is essentially the Bible of the field. If you need to get a result, a theorem, or anything about elliptic curves, you will find it here. There's no, wrong one. There's the mathematics of public key cryptography, which is just very, very handy for a lot of stuff. So, for example, it's got very good references for literally anything that you might want to do. You want to do lattices, you can look into there. You can want to do elliptic curves, you can look into there as well. It has a very good section on the discrete logarithm and the related assumptions, how they're related to each other. For example, whether they also hold with fixed bases. So it has a lot of goodies. On a more historical note, there primes of the form x squared plus ny squared is an incredible book. It essentially tackles the problem of finding primes of that form, which is, that means it's very well named. And it takes the occasion to actually go into the history of number theory and develop the theory behind some of the modern things, which are very useful for cryptography as well. So, for example, they build up to the ideal class group, which is something that is quite important, for example, when computing isogenies, because a lot of the schemes, they make use of those kind of concepts. I've recently got like the computational cryptology, algorithmic aspect of cryptology. This is a very interesting book. Got like a lot of small articles. In particular, there's chapter 5 on computing discrete logarithms, which is very interesting and which has a lot of interesting things, especially with regards to curves which have invalid points. And then there's Nadia Henninger's RSA, DH, and DSA in the wild, which takes a more practical approach on how to actually break the or how schemes are actually broken in practice, which is very interesting. There's a lot of cool case studies and things which went wrong. And finally, there's Algebra Chapter 0 by Alufi, which I think he has a very categorical approach to algebra, which I think is very nice for when you're trying to get a unified view of the things. And it is very much a joy to read. Like the explanations are, they really build a lot of intuitions, and they allow you to touch a lot of interesting topics. It touches on things which are well beyond a standard curricula, and which really helped me. I've taken care of essentially also compiling the details note of where all the results that we have in the book the way the talk were taken from, which hopefully can be helpful. Most of the links should work. There are little references, and I also have some further reading at the end in case you're interested. These are in particularly mostly on the Isogeny case, because that's what I've been looking at most recently, but there are just a lot of very good researches around on the web. So in conclusion, I really hope that you've enjoyed this talk. I really enjoyed compiling the material and giving it. And of course, if you have any question or anything, just feel free to pop a comment or send me an email or anything really. And peace out, I guess.